Hello and welcome. This is Cambridge O-Level Physics paper number 2, theory. The subject code is 5054. This is October-November 2021 paper, and this is the variant 1 for this exam. Let's start. First question, section A, first question. It says the figure 1.1 shows a wooden bench of weight 2000 Newton. Part A, each of the two supports has an area of 0.04 meter square in contact with the ground. Calculate the pressure on the ground due to the bench. So here we are given a bench, and that bench, then the dimensions of that bench are given, and the supports for the bench are also shown, and the weight of the bench is also given to us. So let us first draw a single line diagram of the bench and see how it looks like. So say this is our complete bench. This is the whole length for this bench is 2.2 meters. Our first support is at a distance of 0.25 from here. Say this is our support 1. We call it as Q. This is our support number 2 over here. So again, this is also 0.25 meters from here. Weight of the bench is acting downwards at the center of the point. So this is weight, and weight is 2000 newtons. And the center point, let's call it X. X is at 1.1 meter from it. So basically, we have to find out what is the pressure that is exerted on these two supports, or basically the pressure that is exerted onto these two supports, and say this is the weight that is acting downwards. So we have basically a symmetrical blank or a symmetrical wooden bench, and the weight is 2000 Newton. And from the symmetry, we can easily assume that, when we can see that the weight is equally distributed onto these two planks. Also, we can say from the moment law of moments that this distance is, or both, or this distance, say A and B are equal, and it means that our weight is equally distributed onto these two planks. So basically we have 1000 newtons acting here and 1000 newtons acting here. So the pressure on the ground due to the bench, the pressure will be simply the force per unit area. So this is, for example, the whole area which is given to us. This area is 0.04 meter square, and we know that pressure is equal to force per unit area. So the force acting over it is 1000 newtons divided by 0.04 meter square. So we will get around 25,000 pascals, or we can say that 25 kilopascals. So this is the pressure that is exerted on the ground due to the bench. So pressure is 25,000 pascals is equal to 25 kilopascals. Okay, next part. It says the center of mass of the bench is 1.1 from the left hand end of the bench and is 0.024 meters from the front. So basically, if we see the plank is something like this. So this whole dimension is 0.48 meters, and the overall length is 2.2 meters. So this is a symmetrical, remember it is a symmetrical shape, or a rectangle to be, or a rectangular shape to be very exact. So in such a case, if you want to find out the center of mass, we basically find out the center of this shape, and the center of the shape comes out to be something like this, and this is technically the midpoint of this. So this is 1.1 meters from here and 0.24 meters from here, and this is what this it is said that is the center of mass. It says that suggest one reason why the center of mass is in this position. So remember that for any geometry for remember that for any symmetrical shape, the center of mass lies inside or lies inside or within the shape or the body, within the shape or the body which is concerned. And also the center of mass is the geometrical center of a symmetrical shape. That is why we can say that the geometrical center for this wooden plank lies something like this. And if we have to find the center of mass, it will lie inside the uh, the wooden plank, and since it is balanced, it is perfectly well balanced over these two wooden poles. So we can easily say that this is how a symmetrical shape will have the location for its center of mass. Next part, it says there is a force exerted vertically downwards from the point P as shown in figure. Calculate the maximum force that can be exerted vertically downwards at P without rotating the bench about the point Q. So basically it is saying that this is a bench, and the vertically downward force is exerted over here, and they want to calculate this force F, and the moment across which, or the point across which they want to calculate this force is somewhere here. This is the Q point, and across this point they want to say how much force they can exert over here before tilting this bench or making this bench come out of equilibrium. So the situation we have is something, or if we draw the line diagram, we have something like this. So this is our point Q, this is our point P. We are exerting a force F over here. The center of gravity, or is the point where weight is acting. Weight is 20,000 newtons. This distance is 1.1 meters. This distance is 0.25 meters. So just uh, taking moments across moments across the point Q, we get, so we have clockwise anti-clockwise moment equals to clockwise moment. So anti-clockwise moment will be force multiplied by 0.025 meters. The clockwise moments would be 2000. The weight acting downwards multiplied by 1.1 meters minus 0.25 meters, the distance, or this distance basically. So the force effective would be 2000 multiplied by 0.85 divided by 0.25. The force will be, we are going to calculate this force. This force will be equal to 6,800 Newton, or 6.8 kilonewtons. So the maximum force that we can exert at P that is acting downwards is 6,800 newtons, equals to 6.8 kilonewtons. Remember, do not forget to write the units in your answer. This, you may lose some marks if you're going to miss this point. Next part. In Question number in figure 2.1 shows a man of mass 80 kg standing in a lift or an elevator. The gravitational field strength G is 10 Newton per kg. Calculate weight of the man. So weight equals to mass times gravitational constant strength field strength. So mass is 80 kg multiplied by 10 Newton per kg, and this thing comes out to be 800 newtons. So the weight is 800 newtons. So weight of the man is 800 newtons. Next part. So the lift accelerate upwards uniformly at this. So the acceleration upwards is 0.5 meters per second square. Calculate the resultant upward force on the man. So resultant upward force will be force times mass into acceleration. So mass is 80 kg multiplied by acceleration 0.5 meters per second square. This comes out to be 40 newtons. So kg meters per second square is newtons. So the newtons or 40 kg meters per second square. Both the units are the same. So resultant force acting on the man is 40 newtons. Then part 2, force exerted on the man by the floor of the lift. So see, remember, this is, for example, the man that is standing on the floor, and the weight of the man is acting downwards. This is the weight that is acting downwards. The lift is accelerating upwards. So the upward force upward is uh, 40 newtons, and this is 800 newtons. So this man will be opposing this force. So technically another force of 40 newtons acting downward. So the overall reaction force acting on the man is 800 newtons plus 40 newtons. So it will be 840 newtons. So the overall force or the reaction force exerted by the floor on the man is 840 newtons. Right. So next part question number C. It says the lift accelerates upward uniformly from rest at for 4 seconds, then decelerates uniformly to rest in 4 seconds. Find the total distance traveled. The total distance traveled is 8 meter. On figure 2.2, sketch the distance time graph for this journey. So remember, in a distance time graph for the first 4 seconds, uh, the lift accelerates upward uniformly. So it's an acceleration and it's a uniform acceleration. So it is something like this. It is a curve that accelerates uniformly, and say this is the time. So this is say 4 meters. So we can go up to this point. So this is a uniform acceleration curve, and then it deaccelerates uniformly. So it deaccelerates, it means that it goes something like this. This is a deacceleration curve. So deceleration curve. So eventually after 8 seconds, the distance traveled is 8 uh, meters, and after 8 meters it becomes same. So no distance is further traveled, and so the body is at rest. So remember, the uniform acceleration distance time graph looks something like this. Similarly, uniform deceleration graph looks something like this distance time graph. So this is how we basically make this graph, or this is how this graph will look like. So there is a curve. Remember, make it a curve. Do not make it a straight line. So this I've tried to make it a curve. So let me draw it in a better manner. So for example, this is how it looks like. This is a curve, and then this is another curve that decelerates. Okay, so this is how your graph will look like. Next part. Question number 3, it says a nuclear reaction takes place at the center of the sun. The reaction releases thermal energy. State the name of the type of nuclear reaction that takes place at the center of the sun. So it's a very simple part. This is the nuclear fusion reaction. Or just simply write nuclear fusion reaction. Then part B, thermal energy is emitted from the surface of the sun into the space. The energy is transferred through vacuum of space by thermal radiation. Describe the radiation that is emitted from the surface of the sun. So the sun basically emits electromagnetic waves, and electromagnetic waves are transfers in nature, or electromagnetic radiations are transfer in nature. So we'll write this thing as the sun emits electromagnetic radiations. These are transverse in nature. These are transverse waves or transverse in nature, and consists of you can say the entire electromagnetic spectrum known to humans. So of entire electromagnetic spectrum, uh, including, or for example, such as ultraviolet, uh, ultraviolet radiation, visible light radiation, visible radiation, in infrared radiation, microwave radiation, etc. Right? So this is what it goes, and generally we can also say that these radiations are basically generated because of the nuclear fusion reactions that are taking place on the sun, and within this nuclear fusion there are these radiations that are emitted. Then part two, state the speed of this radiation in vacuum. So speed of this electromagnetic radiation, or is equal to the speed of light. So this is equal to c. C is 3 into 10 to power 8 meters per second approximately. Remember, this is 299798347 meters per second. So just simply write 3 into 10 to power 8 meters per second, and that would be a very good estimate or a good answer, that and that will be acceptable. In the next part, it says the Earth is 1.5 10 to power 11 meters from the surface of the sun. Calculate the time taken for the radiation to travel to the Earth. So we remember that distance equals to speed multiplied by time. So the speed is, we have to basically calculate time. So our distance is 1.5 into 10 to power 11 meters, and speed is 3.8 into 10 to power 11 meters second. So this is 500 comes out to be seconds, and this is approximately 8.333 minutes. So the time taken by this radiation to travel to Earth will be equal to 500 seconds, or 8.333 minutes, right? Then part C, it says explain one advantage of wearing white clothes on sunny days. So remember, white color is poor absorber of heat, or you can say light, and also a good reflector of light. This keeps the body cool on sunny days. So just simply a poor absorber and a good reflector of heat radiation or light is a good option, good answer for this, and that basically keeps your body temperature in check. Then question number 4, it says in a coal-fired power station, coal is burned and electrical energy is produced. State the form of energy in coal that is transferred to electrical energy. So remember the whole process. It is the chemical energy stored in the coal. Chemical energy that is stored into the coal is converted into heat energy. That heat energy is then converted into the mechanical energy of the turbines, and then that mechanical energy of the turbines is converted to the electrical energy or the electricity via generators. Okay, so just the answer is chemical energy. Part B. Part B, its first question, it says, state the principle of conservation of energy. This principle is simple. It says the energy cannot be created or destroyed, or you can say that the law of conservation of energy states that the that energy cannot be created or destroyed. It can only be converted from one form to another. Thus, the overall energy remains constant. So, right? So you can always paraphrase it in your own words. Just simply say the law of conservation of energy, or the principle of conservation of energy states that the overall energy remains constant. It can either be created or destroyed, and can only be converted from one form to the other. Okay, so next part. It says the quantity of electrical energy produced by a power station is much less than the quantity of energy in coal that is burned to generate the electricity. Explain why this is so. So during burning of electricity, energy is lost in the generation system in the form of heat losses, mechanical losses, right? This is lost in the form of heat losses, mechanical losses, uh, uh, some energy is converted into light energy losses. Even when you convert it into electricity, there are some losses, or you can call it electrical losses in the generators, losses, etc. And then there is our other heat exchanging losses, or losses via tubes and pipes, and then something like energy. A lot of energy is lost in generation system in the form of heat, mechanical losses, light energy loss, electrical energy losses, etc. So this is why the overall efficiency of the system decreases. Then part C, it says that state one environmental consequence of generating electricity in coal power plant. So remember, the byproduct is carbon dioxide, and in some cases carbon monoxide, where you do not have complete combustion, carbon monoxide. Uh, these gases cause greenhouse effects resulting in global warming, uh, acid rains, uh, you can say sea level rising, etc. So these are, I mean, this is a very generic statement which covers quite a few basic environmental consequences of using for coal-fired power plants. So okay, so next question, question number 5. It says a plastic rod is initially neutral, is rubbed with a woolen cloth. After the rod has been rubbed, it is positively charged. Explain in terms of particles why the rod is now positively charged. So basically what happened was that during with the help of with friction causes the electrons. So friction causes electrons to be transferred from the rod to the cloth, thereby making the rod positively charged. Okay, so the particle that transfers or moves are, you can say, electrons. Part 2, state what happens to the woolen cloth. So the woolen cloth becomes negatively charged. The woolen cloth becomes negatively charged, right? So next question part. Part B, it says uncharged conducting sphere is suspended from an insulating thread. The positively charged rod is placed near the sphere as shown. On figure 5.1, so on this figure we have to draw the distribution of charge on the sphere. So remember what happens here is the electrostatic induction. So this positive charge rod induces negative charges on the side, on this side of the sphere, whereas the positive charges move on the right side of the sphere. So remember, the good way to draw is 1 2 3 4 5 6 charges are here. So good way to is to have less 6 or less than 6. So I'll draw 5 3 4 5 negative charges here, and equivalent positive charges 1 2 3 4 and 5 are over here. So this is a good way to, or a good practice to draw this. You can draw 5 4 5 or maybe 6, not less than 4. It would be good. So this is how the charge distribution on this sphere looks like, and this phenomena is called electrostatic induction. Electrostatic induction. Okay. Next part, explain why the sphere is pulled towards the rod. So this sphere is pulled toward the rod because the negative charges are induced on this side, positive charges are induced or moved away to the other side, and these negative charges are attracted towards this positively charged rod, and this basically results in a force towards the or in a force in this direction, and thus the sphere is attracted to the rod. So just write it in terms. So you can say that the positively charged, we have to basically write this in words. So we can just simply say that uh, the positively charged rod induces negative charges on the left half of the sphere adjacent to the rod. The opposite charges attract each other, resulting in a force pulling the sphere towards the positive rod. Okay, this is how you can just simply write this. Okay, so next question, question number 6. Question number 6, it says a circuit contains a battery of electromotive force or EMF 4.5 volt, a 28 ohm resistor and a variable resistor. Figure 6.1 is the circuit diagram. Part A, the battery consists of 3 identical cells in series. Determine the EMF of each cell. So 3 cells, total number of cells 3. So EMF total is 4.5 divided by 3. One cell EMF, one cell, and this comes out to be 1.5 volts. EMF of each cell is 1.5. So these cells are connected in series, so just simply divide it by 3, you get your EMF. Then it says the potential difference across the variable resistor is 2.5 volts. State what is meant by the potential difference. So potential difference is the work done or energy required to move a unit charge across the circuit from one point to another point. It's better to say across to move a unit charge completely across the circuit is called, is known as potential difference. So in other words, we can say that the energy required or work done to move a unit charge completely across a circuit is known as the potential difference. Okay, so then it says part B, it says part B, question 2, it says calculate the resistance of the variable resistor. So what we have, so we have a 3-cell battery, we have say a variable resistor here, we have a resistor, normal resistance over here, this is 28 ohms, and the voltage appearing across this 28 ohms is 2.5 volts, this is 4.5 volts. So this is R, call it RV. So so this is a series circuit, so the current in this circuit will be same across this resistor and this resistor. So we just simply find out current through 28 ohm resistor. This current is V divided by R. So voltage is 2.5 divided by 28, and this value is 1 by 14. There is one. Sorry. Sorry. This is the voltage across the variable resistance is, this is 2.5 volts. So this voltage will be the remaining volt, or that this voltage across 28 volt will be 2 volts. This voltage will be, so 2 volts will be appearing across 28 volts. So this will be 2 volts. 1 by 14 amperes. So this is the current that is flowing through the whole circuit. So so the resistance R variable is voltage across this resistance multiplied by the current that is flowing, or just simply no, sorry, my bad. Using Ohm's law, we know that Ohm's law V equals to IR, just this the same one we have used. So R variable is V divided by I. So voltage that is appearing across this variable resistance 2.5 volt divided by current, that is 1.5, 1 by 114 amperes. So this value comes out to be 35 ohms. So my resistance will be 35 ohms in this case. Okay. Next question part. Question 7. The question 7 has two different parts. In first part, it says that you either have to solve this question, or the second part that we have to solve is regarding to the electronics portion. So let's see. Let's solve sequentially, and we will basically do not have any option to uh, skip any part. So we'll be solving all the questions in this uh, video. So it says in figure 7.1, it shows a solenoid connected to an ammeter. So, so this is the solenoid. This is a permanent magnet that is moving inside the solenoid. The south pole of the magnet moves towards the left end of the solenoid. The ammeter reading shows that there is a small positive current in the circuit. Explain why there is a current in the circuit when the magnet moves. So remember, when there is a permanent magnet, so this permanent magnet will have certain magnetic field from north to south, right? So the magnetic field will be emitting from the north and going to the south, and as this magnet moves inside the coil, these magnetic field lines cut this coil, and that cutting of these magnetic field lines results in change of flux across these conducting coils or across the solenoid, and that change in magnetic flux results in production of EMF. And since we have a closed circuit across this solenoid, the changing magnetic flux that is producing EMF in the circuit, in a closed circuit, that results in a current uh, in a circuit. So we have to basically write down this whole aspect in our words. So first, so we can just simply say that moving magnet results in time varying magnetic field. So if you are moving this time varying magnetic field across the solenoid, this results in time varying change in flux in magnetic flux across the conductor of the solenoid. This results in generation of EMF, which leads to generation of which leads to flow of current in the circuit, which is picked up, seen by the or detected by the ammeter, right? So you can just simply write this in this fashion, or you can use your own words to write this whole phenomena as well. Then part B, it says that when the magnet is inside, it stops moving, then it is pulled back out of the solenoid. Explain what happens to the ammeter reading as the magnet moves out of the left end of the solenoid. So remember, so if we are basically moving the magnet out, so it will create the same phenomena, but in this case, the magnetic flux will be changing in the opposite direction, and because of the Lenz's law, uh, the direction of the current will be opposite to the direction of current when as compared to when the magnet was moving inside the solenoid. So we can just simply say that the direction of the current reverses direction of the current reverses and the ammeter uh, shows uh, or if shows opposite value of current or opposite value of current, or if say if the ammeter have a needle, the needle points in the opposite direction, shows opposite value uh, opposite value. uh, this is because the magnetic flux or the magnetic flux, this is because the magnetic flux changing in the opposite direction compared to the previous case, thereby inversing or reversing the polarity of the generated EMF in the solenoid coil, right? So this is how you can just simply explain what's happening in this phenomenon in this case. The, the other option or the other part which we are allowed to, which we are given a choice between, is to solve this part. So it says that figure 7.2 shows a symbol of a logic gate and its truth table. So this is a logic gate. So input is it. So if it's a say A input, this is B input. Both input are zero. The output is one. In either case, all the outputs are zero. So this is basically the inverse of. So if it is an OR gate, so remember the OR gate looks something like this: A, B, X. So OR gate, either A or B is zero, any of the input is one, the output is one, and this is the inverse of this gate. So this output is the inverse of OR. So this is logic NOR, or you can say it it is a NOR gate, right? Then comes part B. It says figure 7.3 shows two pieces of logic gates connected to make a bistable circuit. So remember, this is what we have seen an OR gate in our previous slide. So there is a combination of two OR gates to make this bistable circuit. So here we have terminals P and Q each having logic level 0. So we have P0, Q0, and terminal X has a logic level 1. So the X has a logic level 1. Question 1 says explain why terminal Y has a logic level 0. So why we have a 0 here. Okay. So if X is 1, so X is the input of, say we call it gate B, we call it gate A. So input, oh sorry, X is input to gate B, that is uh, so sorry, the X is input to gate B, that is 1, along with Q equal to 0. So thus, so for using the truth table For NOR gate, the output Y is equal to 0. So the output Y is equal to 0, because we can see that if any because these belongs to these two cases. So any of the input is either 1 or 0, the output will be 0. So this is that what that is happening over here. Next part, it says that terminal P is briefly connected to logic level 1. So terminal P is so initially what we are having a 0 here, we are having a 0 here, we are having a 1 here, we are having a 0 here. So what happens here, that initially it is for temporarily it is connected to a logic level 1. So what happens here? So if it is connected to one state, the effect of this logic level to the terminal X and the logic level of terminal Y. So what will happen here? So if this is connected to 1, the other input is 0. So 1, 0 will have, sorry, so so this is angle, so this is logic 0, this is logic 1. So the output will become logic 0. So what will the effect on the terminal? The terminal X becomes 0. So if the terminal X becomes 0, so the both of these, so this input becomes 0, and resulting in uh, uh, resulting, so we just simply say the terminal X becomes 0. uh, this makes both inputs, so I call this gate B, gate A of gate B to become 0, 0, 0. This makes terminal Y equal to 1. So terminal Y becomes equal to 1, and terminal X becomes equal to 0. Next part, it says terminal P returns to logic level 0 again. In the same terminal, what happens here is that you have gone to 0 again. So what will happen? So if you go to 0 over here, and a 0 is also coming from this point, so the output will remains. State what is the effect of logic level 0 on the terminal X. So the terminal X will remain 1. So X will remain, or you can say, or retain its previous state, that is 1. So if 1 is here, 1 comes here, 1 comes here. Oh, sorry. Let me look at it again. So this one, this X was initially at 0 before this. So now terminal P returns to logic 0 again. So terminal P goes to logic 0 again. So this is logic, so P is logic 0. My this Y was previously 1, so my X will remain 0. So terminal X will be 0, 0. Then the logic level at Y will remain at 1. So basically what happens is the previous state is retained. So the previous state is retained. This is what happens. So state the fact of this logic 0 on the logic level of terminal X and the logic level of terminal Y. So technically there is no effect. The previous state is retained. Then question is state how this circuit exhibits a property of memory. So exhibiting a property of memory, just consider part 3. What happened in part 3 was that we changed the input of P uh, from 1 to 0, and we saw that nothing happened at the output. The output retained whatever the previous values that were stored over there. So this is basically the concept or the property of memory that has been shown here. So we can say that uh, if we have a, or we can say that what this point is 1 at one point. So the logic at P. So I'm just rubbing these and showing you this, that if my logic P has a 1, and my output will retain the value of 1 for that case. If my Q becomes 1, my output Y will also will become 1, and if we change the value of Q for some time, then the value of output won't uh, uh, so change. So just simply see in this case, say what happened here initially. So initially we have uh, P and Q both as 0. So this is 0, Q as 0, and output as 1, right? So my X was equal to 1. So this was 1. So my Y was equal to 0. So my Y was 0. So this was my initial state. So when this initial state was given, 1 was given, Y is here, Y goes over here. So this 0, 0 becomes X equals to 1. So this is how what my initial case was. Then my P changed from 0 to 1. So my P changed from 0 to 1. What happened was that my X goes to 0. So my X went to 0, and my X went to 0. So X 0 will come over here. So 0, 0, and my Y went to 1. Right? So we saw that when 1 is applied here, my X changed its value to 0, my Y retained its value, Y became 1 over here. And now from 1 I change it again back to 0. So for that 0, what happened here is that my Y was 1, here was the 0. So my X is now retaining the value of 0, which was here in the previous case, and this goes here, this goes here, and my 1 has been retained. So this is the what exactly is happening in the memory. So we can say that the output X and Y connect, connected to corresponding inputs P and Q shows which of the input last had 1. That is the concept of memory over here. So we can say that uh, the output X and Y are connected to inputs P and Q respectively. The outputs shows the output show which of the inputs last recorded or last had one. That is what exactly it has been showing, and that is the concept of memory that comes from these bistable circuits. Okay, next. So next we have the section B for this paper. In section B, generally we are given 3 questions, and out of these 3 questions, we have to solve any 2 of the questions. So here we will be solving all the 3 questions for our viewers. So question number 8, it says a loudspeaker is made up of a coil from a coil of wire fixed to a cardboard. The tube is attached to a cardboard cone. Figure 8.1 shows the arrangement of the loudspeaker. When there is a current in the coil experiences a force. State what else is needed in the loudspeaker to make the current carrying wire experience a force. So remember, the current carrying conductor inside a magnetic field results in a force. So we need a permanent magnet or we need a magnet or magnetic field in the case of loudspeaker to generate a force or generate vibrations in the cone. Then part B says the student it says the student connects the coil to the output of an alternating current generator. Figure 8.2 shows the electromotive force produced by the generator with time, right? The coil, tube, and cone vibrate back and forward. Explain why EMF shown in figure 8.2 makes the coil vibrate. Okay, so basically, we have shown an EMF or a electromotive force over here. So this EMF is basically producing a time varying signal, or it's a time varying. It is a time varying signal of EMF that is shown here, and this EMF results in a time varying current that is generated inside the uh, uh, coil or that is wound on the cardboard tube. And if there is a time varying current across a magnetic field, that creates a force uh, and that basically creates a oscillating or time varying force on the uh, cardboard tube, and that basically that basically results in oscillations of the uh, uh, coil back and forth, and that is the cause of vibration. We basically have to write this thing in words, so that it says that the EMF results in a time varying current. So we have the EMF results in time varying current. Uh, the time varying current in present in the presence of magnetic field results in an oscillating force acting on the current carrying conductor, thus making the coil to vibrate. Okay, so this is how the coil vibrates. Then in next part, it says that the vibrating cone produces sound in the surrounding air. Explain in terms of molecules how the cone produces a sound wave that travels through the air. So remember, so this is our cone, uh, and if it moves forward, it basically compresses the air. Compresses the air, and if this cone moves backwards, again, if this cone moves backwards, it decompresses the air or causes rarefactions. So it calls rarefactions or decompressions. And this back and forth movement of this cone basically results in this compression, rarefaction, compression, rarefaction, compression, rarefaction, and that allows the sound waves or to propagate uh, in all directions, or in the direction, or in that is specific to the loudspeaker, or in a direction in which the loudspeaker is moving. And also the sound waves are longitudinal waves, so the directional or the vibration of the molecules is in parallel to the direction of vibration of the uh, uh, this uh, cone of this loudspeaker. So you can say that in terms of air, so it says explain in terms of molecules. So we have to explain this in terms of what happens to the air molecules, how cone produces a sound wave that travels. You can say that the vibrations of the cone corresponding to the sound perturbs the air molecules, resulting in compression and rarefactions. Right? This continues with the uh, you can say the vibration of the cone, thereby generating sound waves. Uh, you can say that sound waves, or in terms of energy, so the energy from these, so the energy from the compression and rarefaction of air molecules is transferred to the adjacent molecules, so to the adjacent air molecules, resulting in propagation of sound. So, okay, so you can write this in terms of compression, rarefactions, and the movement of coil produces this. And since this is a continuing motion, so this rarefactions, compressions, then rarefaction, then compression results in transfer of energy to the adjacent air molecules, thereby resulting in propagation of sound or production of sound. So question part 3, it says that sound is a longitudinal wave. Describe the difference between a longitudinal wave and a transverse wave. So for a longitudinal wave, remember the particles move in parallel to the direction of propagation of the wave. For transverse wave, particles move perpendicular to the direction of propagation of the wave, right? So this is how, or this is exactly the difference between a longitudinal and a transverse wave. So next part, question number 4, it says that you using figure 8.2 determine the number of times the cone reverses its direction of motion in 1 second. Okay. So here we see that one time period is equal to 0.05 seconds. So we can just simply say that time period is 0.05 seconds. So we can calculate frequency from here as 1 by t. So 1 divided by 0.005, this becomes equals to 200 cycles per second or 200 hertz. So in one cycle, it, that twice the change in direction, or twice the change in direction. So in 200 cycles, 2 into 200, that is equal to, sorry, 400 times. So it basically changes its direction 400 times, right? So this is how we can just simply say that. So the next part, question 5, or sorry, part 5, it says the speed of sound in air is 340 meters per second. Calculate the wavelength of sound. So remember, V equals to F lambda. So frequency to us is 200 hertz. Lambda we have to calculate, and velocity of sound is 340 meters per second. So lambda is 340 divided by 200, it is 1.7 meters. So the answer is 1.7 meters, right? So this is how you calculate the overall frequency or wavelength of the sound. Next part C, it says the student adjusts the generator so the maximum voltage of the output is now 3 volts. Everything else remains stays the same as the output is shown on the curve. Explain explain any effect on the loudness of the sound. So remember, if we go back and see this curve, so this curve, the amplitude of this curve is something. Where is my marker? So the amplitude of this curve is something around 3.8 volts. So it has been decreased to somewhat around here. So 3 volts is here. So the amplitude has been decreased to 3 volts from 3.5 volts. So we can say that uh, the loudness is directly proportional to amplitude. The amplitude has been decreased from 3.8 volts to 3 volts. Thus, the loudness decreases. Okay. Then it says question C, part 2, any effect on the pitch of the sound. So remember, pitch is proportional to frequency of the sound. There is no change in frequency, thus the pitch remains the same, right? So this is how we write this answer. Then question number 9. In question number 9, it says that liquid in glass thermometers use the expansion of liquid to indicate the temperature. In figure 9.1 shows molecular structure of a solid and a gas. Part A, here we are shown a solid. We can see a regular arrangement of atoms or molecules. In gas, we see random and arrangement of molecules, and they are far apart from each other. In part 1, it says in the middle box, sketch the diagram to show molecular arrangement of a liquid. So for when we have to do a molecular arrangement of liquid, we have to draw molecules which are loosely packed but close to each other. So loosely packed, so we may have 4 over here, somewhat here, 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 something like this. So we can have or something like this to show that the arrangement of molecules is much relaxed compared to solid, but not as random as gas. They are loosely packed but close together and conform to the shape of the liquid. Then it says explain why it is easier to compress a gas than to compress a solid. Remember, in gases, molecules are far apart loosely packed with weak intermolecular forces. However, in solids, the molecules or atoms are closely packed with strong intermolecular forces. Intermolecular, also called interatomic forces. This makes them difficult to compress as compared to gases. Yes. So if you are going to compress gas, the molecules are loosely packed or randomly placed, randomly moving far apart. So you can just simply easily compress them together with the help of force, but the molecules are already densely packed and you can say closely packed with strong intermolecular forces, and therefore it is difficult to compress solids to or compress solids further into any other state. So then part 3, it says the temperature in a liquid in glass thermometer increases. State two ways in which the molecules of the liquid in a thermometer are affected. So the temperature has been increased, so the molecules basically will start vibrating more vigorously. So there are multiple things we can write. Um, Molecules more vibrations move far apart from each other. We can also say increase in temperature of these molecules. We can also say um, molecule molecular forces are weakened. So, I mean, more vibrations of the molecules move far from each other, the overall temperature increases, then the molecular forces are weakened as well. So there are multiple points we can write on what happens to the molecules of the liquid inside a thermometer. Then part B, it says figure 9.2 shows liquid in a glass thermometer. There is no scale on the thermometer. So state what is meant by the ice point and the steam point. So ice point is basically a point where uh, water and ice are present at the same time, uh, or you can say at the same time, or are at equilibrium, or basically talking about ice and water. Um, this is you can say melting point, right, of ice. So at melting point of ice, both ice and water are present. That is equal to 0 degree centigrade. Steam point, again, in this point, water and steam are present in equilibrium. Again, just like the uppercase, instead of ice, we have steam. Now this is basically the boiling point of water. So remember, and that boiling point is at 100 degrees centigrade. So at boiling point, we have both steam and water present at the same time. Okay. So next part, describe how ice point and steam point are used on a thermometer. So remember, ice point and steam point are two ends of. So ice point is the 0 degree calibration on a thermometer. Steam point is the 100 degree C calibration on a thermometer. Uh, and we can say that what you can say the difference or the uh, the intervals between them, or you can say the length slash interval between these 2 points is further divided into uh, or marked into um, units of maybe say 1 degree centigrade or 5 degrees centigrade or 10 degrees centigrade, depending upon the type of the thermometer we have. So basically, the ice point and steam point are two endpoints on a thermometer or a liquid and glass thermometer, and they basically give you the length in which you can easily measure the expansion of liquid, or and basically relate that expansion of liquid to the change in temperature. Expansion or contraction of a liquid related to the increase and decrease in temperature of a liquid, or the surrounding against which the thermometer is used. And then question number part C, it says explain how range of a liquid in glass thermometer be affected by increasing the mass of the liquid in the bulb. So remember, if we increase uh, the mass of the liquid, the overall range will decrease, because what happens is that we have more mass available, and in case of rise in temperature, we have more expansion of liquid into the tube, and that basically, if we have the same, of if we have a if I have a thermometer that is calibrated for m amount of mass, and if we increase the mass by twice, so the range we have, say for example, if we are able to measure 100 degrees, may not be able to measure 100 degrees, because the rise in temperature or decrease in temperature will result in more further expansion of liquid into, or mass into the calibrated tube. So this is what we have to write. So we can say that uh, the range decreases as more liquid expands in a given length for same rise in temperature. Okay, then it says what happens if we increase the diameter of a narrow tube. So if we keep everything the same and we just increase the diameter of the narrow tube, what will happen? So in this case, our range will increase. The range will increase as more liquid uh, will be, or more liquid or more volume of liquid will be required to reach the same calibrated height for a more for same rise slash decrease in temperature. So remember, generally the range is directly proportional to the square of the diameter of the tube. So diameter of this tube. So basically on a same calibrated scale, if we increase the diameter, so the range is decreased by you know under root of 2 times. Okay, so next part, it's a question number 10. It says the isotope yttrium 90 or Y90 by 39 is a radioactive. It is a beta particle emitter that decays the product to Q. The product Q is stable. State one feature that is common to all isotopes of yttrium. So remember the definition of isotopes. Isotopes have same number of protons but different number of neutrons. So the common feature, you can say that they have same number of protons but different number of neutrons. So you can just simply say same number of protons. Okay, so again, now we have to describe how neutral atom Q differs from neutral atom of yttrium 90. So remember yttrium 90 39, it decays, it basically emits beta particle and becomes Q is 90 40. So the Q is 90 and 40. So um, what is you can say how the neutral atom Q differs from neutral atom of yttrium 90. So it has basically one more neutron. So basically Q contains one more proton. It has one less neutron and have one more electron. So these are the three differences contains this compared to yttrium 90 by 90 or yttrium 90 for compared to yttrium 90. The neutral atom Q contains one more proton, one less neutron, and one more electron, and this can be seen from this equation as well. Then question number part 10 part C, it says that a sample of yttrium 90 is placed close to a radioactive detector in a lab. There is no radioactive samples in the lab. The counter records the rate. So this is the recorded rate. Using 10.1, determine the background count. So we can see that the yttrium 90 has decayed and then the result has been stable. So this is the decay that is or the radiation detector counter is constantly measuring this after the yttrium 90 has passed its complete half-life or is completely decayed. So we can find out this value, and this value is something like here, so approximately equals to 18. So the average background counts is 18 counts per minute. The average background count is 18 counts per minute approximately from the graph. So part 2, it says suggest two different sources of this background count. So this is we can one can be cosmic slash microwave radiation or cosmic microwave radiation, or part 2 those can be presence of radioactive material in the surrounding. It can be because of anything. It can be surrounding material. Then it can be a nuclear. You can say it vicinity of a nuclear test site. Vicinity. Okay, there can be radon presence. There can be nuclear material in the uh, land. XYZ. There can be any reason for that. Part 3, it says using 10.1 determine the half-life of yttrium. So determining the half-life of yttrium, initially we determine two count rates. So we call it say n naught. So initially n naught, if we were going to measure, this is 75 counts per minute, and just make it half. So half would be around 37.5 somewhere here. So half would be around 37.5, and at 37.5 we can see that the time is around 100 hours. So at 100 hours we can see that this is around 37.5. So this is 37.5 per minute. There are two values, so we use these two values. So we say that, so that initial n naught is 75 counts per minute, and the second after time t we have 37.5 counts per minute, and time here is 100 hours. So time here is 100 hours. So now the formula we have is generally that is used is nt, and not 1 by 2 half life t divided by t half life. So this is the formula. So one of the common mistake a student makes over here is just to put in these values and calculate. This is wrong. So always use background count. How we are going to use the background count? So n naught is 75 minus 18. So this is the my value of n naught, and nt will be 37.5 minus 18. I'm going to minus out these values. So 75 minus 18, my actual count rate is 57 counts, and 37.5 minus 18 is approximately equal to 19.5 pounds per minute. These are the actual values which I'm going to, or which we have to use in this formula. Using these values, we get 19.5 divided by 57. 1 by 2 time is 100 hours divided by t half life. So just so t half life, if you're going to solve this, taking log on both sides and just simplifying it, so t half life comes out approximately 64.620 hours. So half life approximately 64.620 hours, or you can say 65 hours, right? So something like this will be or any value in this ballpark will give you a good answer or the right answer. Okay. Then comes part 4. It says many points on plotted on the figure do not lie on the best fit line. Explain why. So we are basically, remember, we are measuring beta particles. So one reason can be measuring beta particles is difficult. So measuring different beta particles is difficult. Uh, there is some random uh, ness in beta emission. So there is some randomness in beta emission or randomness in radiation as well. There is human error. Uh, there is instrumentation error. So there can be multiple reasons for it.
Uh, so I mean, just random radiation, randomness in beta emission, human error, instrumentation error, measuring beta particles is difficult. So I mean, generally one, two, and three are generally good. I mean, all of these are good options, but these two are more better suited or more technically well suited for answers. Uh, part D it says the stream of beta particles traveling in vacuum enters a region or between two parallel metal plates. One plate is negatively charged and the other is positively charged. This shows it. So remember, beta particles 0 minus 1 are equivalent to electrons, and electrons 0 minus 1 or its electrons are a negatively charged particle. So beta particles, negatively charged particles will move upwards towards the this. So you can call it electron or beta particles. So this is how this will look like. So on the draw taken, path taken by the beta particle as they travel between the two plates. So you just remember, do not make this path very long. So this will be just immediately they will be attracted. So just a you know half a centimeter or 1 centimeter line would be a good choice. So something like this will be a good figure or good drawing to show that what happens to the beta particles. Since beta particles are negatively charged particles, so negatively charged particles are attracted by the positively charged plate. So this is how we draw the negatively uh, the path of the beta particle that is taken by them across this plate. So this is uh, our paper number 2 for October-November 2020 exam. Uh, so if you have any questions, please feel free to message me in the text box. And I wish you all the best for your upcoming exams and your future endeavors. So thank you very much for listening. Bye bye.